I am happy to welcome everyone back to the Wilson Forum, and I'm especially happy to welcome today Professor Srinivasan Chandrasekar from Purdue University. Chandy's a longtime friend of mine, both personally and professionally, and I really am happy to welcome you today, Chandy.
Thanks.
Chandy and I have been collaborating on what I consider to be something of a revolution in manufacturing operations. During much of my career, I've tried to understand and then prevent embrittlement phenomenon from occurring when metals are put into service environments. I've tried to prevent that, try to understand it and prevent it. But Chandy and I have actually been working on a means of taking advantage of that. And in particular, Chandy works on manufacturing operations of a number of different types. But in metal cutting, for example, your object is to produce metal chips, to remove metal, and to produce a surface with a limited amount of energy required to do that, and then to produce a surface that has a magnificent surface finish. And that's a pretty tall order. But what we've discovered is that we can take advantage of what are known as self-assembling monolayers adsorbate on the surface of metals as they're being cut. It causes them to embrittle, and that changes the chip formation process dramatically. This is the first time that I've ever seen something like an embrittlement phenomenon used to advantage. And I really do think it represents something of a revolution in metal cutting. We're going to have to invite Chandy back to talk about that because that's not the subject of his conversation today.
Today it's
I,
all destruction.
yeah, I just wanted to put context around what this guy does. Uh, we're going to hear today about his discovery of the solution or understanding of a 400-year-old mystery. Uh, and I want to tell you that when he found this solution, he produced a video that went on YouTube and has had historically 65 million views. I didn't say 65 views. I said 65 million views. So, Chandy, I'm happy to welcome not only a material science and industrial engineering colleague, but a genuine YouTube celebrity to our group today. Welcome, Chandy. We're looking forward to hearing about St. Rupert.
I'll bite a poor one.
Welcome aboard, Chandy. It's good to see you again.
Thanks, Ron. So I will now screen share,
Yeah.
and, uh, and I hope I can do justice to the.
There you go.
Is that all right?
Yeah, you can probably make that full scale. That's perfect. Perfect. And
Is
Chandy,
this
just for reference, before we actually put the recording up on our website or broadcast it, we do edit. So any of the mechanical issues like this one, we'll edit out. Don't worry about it. But
Yeah,
you're fine to
no
go.
problem. That is you're welcome to put it on for on your site and record, etc. There's no issue.
Great. Thank you, sir.
Okay. So today, thanks, Ron, for inviting me to this forum and to share this work on Prince Rupert's drops that has been going on and off for now 30 years. Whenever there is a break, we revisit Rupert's drops and do something. So that's it started in 92 in Cambridge, England, at the Cavendish Laboratory, or 89 at Purdue, 92 in Cambridge, and then again 2015, 16, 17 over here, and in Cambridge, and in Indian Institute of Science in Bangalore, and Tallinn, Estonia. So that's the different connections. So we'll today I'll share something about the sort of curious properties of this glass drop called Prince Rupert's drops. Um, you see, show some pictures there on this cover slide. These are Prince Rupert's drops. They are lovely looking drops. They look like a tear or a pear, depending on what analogy you prefer. They're made up of a head that is, we'll say, sort of oval or pear-shaped, and then a long tail. These are produced by this is a single drop. Some typical sizes. I didn't put a scale bar, but I gave you the size of the head, which is about 8 millimeters here. Many of these have little vacuoles in them. That these are little voids, and then they have a long tail. So an expert glass blower can produce them quite easily, and they can make beautiful drops from colored glass, whatever glass you give them. And the tail can even be made several meters long. So that's and these are the first examples of what are called toughened glasses. That is, glasses which are very resistant to crack propagation in certain regions. There you find them today all around you, especially in cell phone screens, computer displays. Of course, they were used in car windshields in the early 30s when they were first introduced, and then also in things like bulletproofing and so on. Typically, the drops that we are going to discuss today, except for a few, are all made of soda lime glass. Here is a picture that I took from a book. I'm not giving all the citations because it becomes a little cumbersome, but this is from a book by Holloway, which shows a glass blower holding a glass rod and then holding a flame torch to it. And you see the drop sort of separating from the rod at the top. And then you let it drop into a beaker of water. You have to do this a little bit skillfully because often the drops will shatter as they fall into the water. So the glass blower has to have a certain level of skill, and then also you need to cushion the impact of the drop when it hits the surface by putting in some sand or sawdust or whatever. But now the sort of interesting thing about these drops is that you can take one of these drops and then really hammer them on the head. That is the pear-shaped side, the spherical side. You can hit it pretty hard. I will put some numbers to it later as to what hard means. And the glass will, rarely break. It's quite strong in the head, headstrong. And then on the other hand, if you tweak the tail, if you just snip off the tail, it'll explode into powder with a little pop. So that shows it's extremely fragile when you tweak the tail and very strong when you hammer the head. So it has a unique sort of a curious combination of strength and fragility. So those are actually two different things in the material science, but nevertheless we always view them as maybe something strong is not fragile and so on. So here is a combination of strength and fragility, and this shows the on the right hand side you can see an exploded drop with lots of fragments generated after the explosion, and there's usually a little noise. Now, some history for those who are interested, and I'm sure many in this group are interested in history, both and this history is very also to me it was very interesting. These drops existed prior to 1625. That's documented in the literature. First references in Mecklenburg, Germany. It was very popular on the continent. Lots of people experimented with them, including Huygens, who was very famous as in optics. It was referenced in this book called Traité de Physique by Roholt, which was the standard textbook till Newton appeared on the scene, and then this textbook disappeared into oblivion. A gentleman by name Prince Rupert, a minor prince of the Rhine, brought these to England around 1660 and presented them to King Charles II. Charles was a very strong proponent of science, and you'll see why so in a second. He presented it to them and he demonstrated these properties, but he also told Charles that these drops, I think he brought, were made of colored glass. And so he said that these little vacuoles contained liquor in them. And so Charles was particularly intrigued by that. Of course, that was a bunch of nonsense. But Charles at that time, so he gave these drops to a group of people who constituted at that time what was called the society. They had formed a little group. They called themselves the society. It was based in Gresham College at that time on the outskirts of London. And he told them to explore the properties of these drops and to make some and explain them to him, whether it's putting wine or liquor into the vacuoles or the curious properties. He just said, explain, do your experiments and then explain. So this society in Gresham College, within a couple of years, by royal charter, became the Royal Society of London, and today it's called the Royal Society. And it's the oldest scientific society, and the journal published by the Royal Society, the Philosophical Transactions, and then a branch of it, the Proceedings, is the oldest peer-reviewed scientific journal known to us. At that time, Robert Hooke, who's famous in materials as well as in physics, More, who was the first secretary of the Royal Society, they did a variety of experiments, and a number of famous names have been associated trying to playing around with these drops. So these drops have been known for now close to 400 years and perhaps longer. But the first patents on what are called tempered or toughened glass, they didn't appear till 1873, and they were awarded to a gentleman in England. And then the first use of these drops in practical applications occurred only in the 1930s, in car windshields and so on. These drops, obviously, the head of the drop is very resistant to damage because they have a certain type of stress in them, and so they started being used, and then subsequently various other types of what are called toughened glasses came into being, and you see them. You've heard of things like Gorilla Glass and so on, used in your cell phone screens. So these are all offshoots of this little drop. So 400 years. The drops took nearly 300 years before they started finding commercial use. Some pictures. I'll come to this portrait later. Prince Rupert on the left, and then ostensibly a portrait of Hooke, who was a contemporary of Newton, and Newton and Hooke became bitter enemies. Hooke discovered something called Hooke's law, and then he also laid claim to discovery of the law of gravitation, which Newton took great objection to, and that led to enmity, and that's a different story. So Hooke made a number of observations, and he has a beautiful book called Micrographia. So it's a catalog of observations of both inanimate and animate objects he made with his magnifying glass, and he used the glass and microscope also to observe Rupert's drops. What he did was he encased the drop in fish glue so that when you snap the tail and the drop explodes, the fragments don't fly out. So they stay in place. And then he made a number of observations and tried to deduce why the drops behaved as they behaved. And here is a picture from Micrographia. The left-hand side is one view, and the right-hand side is like a cross-sectional view. And he thought that the fragments were all conical in shape. And so you see them as circles in the left-hand picture in one projection, and then as radial lines in the other cross-sectional picture. And interestingly, I just noticed yesterday that the Royal Society website now has the original Micrographia, which is perhaps one of their first books with their imprimatur, now restored digitally and with all the photographs that Hooke took. And they are just marvelous pictures. And if you have a chance, go in and look at not only Hooke's Micrographia, but number of other early books, and they've done a really wonderful job. They always do, the Royal Society. Now, what we are going to do is, despite much work that all these people did, and subsequently, we felt maybe 30 years ago that there wasn't still a clear-cut explanation of why is the drop so fragile. I mean, people say it's all due to stresses and so on, but why does the drop disintegrate as it does with a pop with lots of fragments? Can we give a clear explanation? And secondly, why is the drop also so strong, and when does it eventually fail when you hammer it on the head with sufficient force? So we decided, okay, the best way to approach the problem of disintegration is by direct observations. Whether we can capture the disintegration of a drop in real time using high-speed photography, and that is going to constitute much of the first 3/4 of the talk. So in order to do that, we first made some drops. We have to make a drop, and then we'll have to, shoot the disintegration with high-speed camera. And then in the process, we have to solve a number of what seems like minor technical problems, but they are actually reasonably challenging. So the drops, we made them by quenching soda lime in a beaker of water, typically 6 to 10 millimeters in the head and a couple of inches long tail. If you go to the Science Museum in London, you will see some of these drops, and the drops there are quite large. They may be as big as an inch in diameter at the head. So large drops. But in order to see the effects in their more spectacular fashion, it's better to work with the smaller drops. They explode better, and the noise and everything else is more impressive. Some information about the elementary properties, physical properties of the drops. Then what we are going to show is high-speed photography of the disintegration using a high-speed camera or a couple of high-speed cameras, and the framing rates will be about in the range of about 5,000 to a couple of million frames per second. And each has its advantage. The low-speed shooting camera shows certain things, and of course the higher speed million frames per second shows other kinds of detail. And we are going to make the drop disintegrate, not usually for the most of the high-speed work, not by tweaking the tail with your hand or fingers, but actually by exploding a 26 milligram lead azide charge. This is a detonator. This is a charge that is used in a detonator, and it's a small charge. So we make a little crack in the tail, and then we'll make the crack propagate by exploding this little detonator, and we'll observe the propagation. So the first experiments are actually going to be not with the lead azide charge, but rather with we'll break the tail by just hitting it with a chisel, and then we are going to observe the explosion of the drop at relatively low framing rates. So this shows a sequence of 4 frames. This is filmed at about 6,000 frames per second. So the time between frames is about 0.15 milliseconds. So you see a drop on the left, 1, 2, 3, 4 is the sequence of the frames. And then as you hit it with the chisel, the whole drop explodes, and this gives you sort of an overview of the explosion. So from this type of a picture, you can get some details like how fast do the fragments fly out. You see that the explosion is spherically symmetric, very much similar to the first atomic bomb explosions. It's interesting because the first calculations of the energy of the atomic explosion was done by a gentleman named G.I. Taylor, and he exploited this spherical symmetry of the explosion to get the estimate of the energy. He was a British scientist, and he did not have any information because the US had classified all the information, and he just did simple dimensional analysis and back of the envelope calculations and the sphericity of the explosion to capture the atomic energy explosion. And in the same way, this one has a spherical symmetry, fragments fly out, and we have also done sort of simple dimensional analysis to calculate the energy associated with these fragments and so on. What you can tell from this is that the fragments come out at about 20 meters per second. These are the particles, they fly out. You can also get the velocity in another way, which is you break the drop and you look at how far the fragments have gone and fallen on the floor. And just by measuring distances and using simple physics, high school physics, you can estimate the velocity of the fragments. And surprisingly, there is very good agreement between what you see with the high-speed photography and the fragment velocities that you get by just mopping them off the floor and measuring distances. The next, obviously, while this captures the explosion, it doesn't tell you, we don't get any detail about how the drop is actually disintegrating inside in the interior. So for that, we have to look, ideally, we would like to look in the inside of the drop and see what is happening there. And for this, this is where the real high-speed photography comes in. So here you see the experimental arrangement. So you have a drop. Some of the experiments will be done in water, and some will be done in glycerine to match the refractive index so that you can see through the drop better. And then some are just done in air. So you have a drop suspended in a chamber. There is a light source at the left, which is a flash tube, xenon flash tube that lights up for about 150 milliseconds. The right-hand side is the high-speed camera. The optics is, the focusing is shown here. And then on the tail of the drop, we make a little notch, and then we attach the detonator, and then we ignite the detonator. This arrangement has some advantage. The triggering of the detonator is done with an electric impulse. Likewise, the triggering of the light source is done electrically. And so is the case with the high-speed camera. So by using since we can use electrical signals to do all these things, the important thing in high-speed photography is always you want to capture the event. Event has to be lit. And then the event has to be synchronized with the filming with the camera. This was done with an analog camera, with film camera. I did this with my colleague in Cambridge in 1991 or so. And the camera itself was a camera that was brought to Cambridge in 1954. And it was a second-hand camera that Philip Bowden was a very famous surface scientist there. He brought it from DuPont, who was getting rid of the camera. So it was already a 40-year-old second-hand camera, but worked beautifully. And what you do is you roll about 100 frames of a film along an arc, and then there's the event is projected on the film, and you can go up to 5 million frames per second in this way, but you'll capture about 100 frames. I won't go into the details of the camera per se, but it's not any digital camera. It's an analog camera with film, and the resolution is just superb if you can synchronize the the event, the lighting, and the capture of the event. So first thing, now we are going to actually the important thing here is we need to see on the inside of the drop, and it turns out when you just light it up like what is shown here, it's hard to see the interior. So what you need to do is between the light source and the drop, if you just insert a sheet of tracing paper or some sort of ground glass, then the light source will be made more diffuse, and that trick lights up the interior. So having a diffuse source, making the light source a little bit diffuse, helps you light up the interior. And when we first reported these experiments, we left out that detail so that we had the advantage of being able to use that to do more experiments before others reported. So here is a picture of a drop. Again, you see the interior lit up in frame 1. This is before anything is happening. You see the vacuoles. And what we are going to do is now trigger the explosion so that a crack starts propagating from the tail, which is in the right-hand side of the drop. And we're going to follow the sequence as to what happens to the interior of the drop. So the sequence goes from 1 through 8. This is done at 500,000 frames per second, so that between each frame, the time is 2 microseconds. So on the left-hand side, frame 1, everything is clear. Frame 2, you just start seeing the crack front coming in from the tail at the arrow. And then if you follow the arrow, you see the crack front moving from right to left. And then by about frame 7, the whole of the interior of the drop has become dark. And that's because the whole drop has fragmented, and light is no longer able to come through the drop onto the camera. And so then you just see a dark drop. So the crack starts appearing in the field of view in frame 2, progresses in 3, 4, 5, and so on and so forth. And the scale bar is shown in the top left. It's 3 millimeters in terms of space dimension, and then it's 2 microseconds between frames. So what you see is a progression of a fracture front from the tail all the way to the left, and by frame 7, the drop is done. Now, what can we learn from this? The main thing is that there's a crack front advancing. Eventually, the crack front propagates all the way, fracture front advancing propagates all the way to the left. By making measurements of the distance between frames and knowing the time interval between frames, we can get the velocity of motion of the fracture front. And what we found was that this fracture front advances at about just under 2 kilometers per second, 2,000 meters per second. It's about 1,700. For reference, velocity of sound in air is about 300 meters per second. But remember, this is not, fracture is not propagating in air, but it's propagating in a solid. And so typically cracks move in solids at about 35 to 40, their peak speed is usually about 35 to 40% of the velocity of sound in the medium. So in glass, a crack would propagate peak speed at about 1,700 meters per second, and the sound velocity in glass is 4,500 meters per second. Quite large. If you,
Chandy, just a question, Chandy. Is it the case that crack propagation always occurs if you have a crack initiation on the tail towards the head, or would a crack initiation site on the head propagate to the tail? Is it always in? Yeah.
Good question. Usually, for this explosion, it's always a crack initiating on the tail, propagating towards the head.
Yeah.
And I'll come to the. It's very hard to initiate a crack in the core of the head without breaking the head.
Okay.
So that question, one part of your question cannot be answered because
Okay, I
it's
see.
physically
Okay.
not possible to do the experiment.
Okay.
Yeah, but here it's always a crack initiating in the tail, propagating in the core. And
Okay.
these drops were speculated, based on the rigorous theory that they were thought to have tensile stresses in the interior and compression in the outer.
Okay.
Okay, so the core is conducive to crack propagation, and people knew that there was tension in the interior, compression in the outside, and that's so the crack would propagate in the core, right? But so I hope I answered that question at least
Yeah, no, that's
partially.
good. That's
Yeah.
good. Okay.
Yeah. So crack velocity is about 1700 meters per second peak velocity, the crack front, and propagates from the tail to the head, and eventually the drop has disintegrated. But now let's see if we can get some more detail so that we can explain how what the mechanism of disintegration is. So if you go and look at this crack front, fracture front in greater detail, what we always found was that at the arrow in the center of the core of the drop on the top picture, we always found what looked like fingers ahead of the crack front. So the crack front is sort of curved, but they're always projecting fingers. So these are features that were visible in practically every front that we imaged. And you can see that also in the bottom frame. So every crack front had finger-like projections protruding from the front. And this is this is more of the same. Another sequence. This is taken at 1,000,000 frames per second. Here again, if you look at the front, you will see finger-like features. So this is characteristic of every fracture front we observed in these drops. I showed one before, and this is another sequence. Here again, it goes 1, 2, 3, 4, all the way to 9. And you see there's a little blob in the middle, which is the vacuole. And the vacuole didn't seem to play any big role in changing the velocity of the fracture front or anything like that. We couldn't measure. So a characteristic feature of this fracture front is always the appearance of these finger-like protrusions. If you look at the front, if you blow up one of these frames so that the magnification is increased, these fronts are seen, and we have recreated these fingers in the form of a line diagram in the top right. So these finger-like features are very characteristic of bifurcation of a crack. So whenever crack travels, it's like in a fork in the road. If it decides to go in 2 or 3 different ways, that's called bifurcation. That bifurcation is always characterized by fingers, finger-like features. So when you see finger-like features ahead of a crack front, it always means that the crack is bifurcating. So 2 things from this very high-speed image pictures. One is the velocity of the crack always reached about 1,700 meters per second, which is roughly 40% of the velocity of sound in the glass. And that is usually a hard limit. And then you always have bifurcation of the crack occurring ahead of the front. Now, this is a picture, a sequence of, again, another high-speed sequence. This is not taken from a Rupert's drop. It's taken from impact of a little tungsten carbide sphere, 2 millimeters in diameter, hitting the surface of toughened glass, bulletproof glass at 150 meters per second. So this is taken in polarized light. Polarized light shows up the stresses. And if you look in the frame 1, Now there are some fringes. It's not important. They're not important, but the black fringe tells you, in this case, the sphere is hitting the block of glass. Light is being shown through the glass, polarized light. And the black fringe tells you that the region above consists of material in compression, compressive stress, and below in tension, pre-stressed. And here again, you see that when the sphere hits the block, cracks are set in motion, and then the crack propagates, and then you see these fingers appear quite prominently here. Right? This is a cleaner system. It's a block rather than a three-dimensional sphere, and so this is just to make the point that crack bifurcation is always occurs in glass when the crack has reached a critical speed. So whenever cracks reach a speed that's, I told you 1700 meters per second, the crack won't accelerate further. It will instead, it finds it easier to propagate by splitting into multiple cracks rather than as one single crack. So that sets the limit to the maximum speed of crack propagation in glass or in any other material. For example, in diamond, of course, the maximum velocity of sound is north of 10 kilometers per second. So this bifurcation would occur at closer to 4 kilometers per second or something like that. So crack bifurcation, and then we also capture this well-known fact that the speed of the crack doesn't exceed what is the theoretical limit in soda-lime glass of 1700 meters per second. This is more experiments in polarized light with the drop showing that even as the crack is propagating, the stresses in the glass revealed by the fringes, the stress field doesn't get perturbed at all till the crack has almost reached a point. So at any point, the fringes stay the same till the crack front actually comes very close to the fringe, and only then you see a distortion in the stress field. And again, you can see some fingering events ahead of the main crack. Now, there are some other questions one may raise. One may say, well, you set an explosion in motion. Were there some stress waves that were set up in the glass that resulted in the fracture and not this phenomenon of a crack propagating from the tail? So here what we did was we did this experiment under water. So the drop's head is seen under water. And in water, you can use a technique called Schlieren photography, which makes use of refractive changes in glass caused by shock waves or stress waves to see if you can visualize whether there were any stress waves, and we couldn't see any. And in fact, that arrow on the top left, frame 1 points to a little bubble that is sticking to the glass surface. And if you come to frame 8, when the explosion is complete, the bubble still stays stuck to the glass. That means if there were stress waves too, they weren't even strong enough to dislodge the bubble. So we ruled out stress waves as the cause, confirming that it's the crack propagation from the tail that is the reason, and the bifurcation. Now, we also did some experiments taking a Rupert's drop and then annealing it. Annealing means we just heat it to a suitable temperature, in this case, something close to the glass transition temperature. And what annealing does is it gets rid of the internal stresses in the glass. So somebody asked the question, I think early on, whether we had done any work with anneal drops. And so this is an anneal drop. And again, the same crack, explosion from the tail. But here the drop doesn't disintegrate. Instead, it just breaks into 2 pieces. So where you see the letter A and then a couple of arrows, little fractures develop, and then the head of the drop just flies off, and the right-hand side, the tail stays intact, and we could actually recover the head intact without any disintegration. So annealed drops don't disintegrate like non-annealed drops. So that again shows that stresses are the reason. And so this is to rule out that the explosion is also the cause of any hanky-panky here. Now, if we now we want to try to reconstruct a picture of how the disintegration occurs based on our observations. So there are two important papers in this crack bifurcation business. The first was written in 1948 by a gentleman named Neville Mott, later Sir Neville. He won a Nobel Prize in physics in 1974 with Philip Anderson and Van Vleck, I think. He did some very simple back of the envelope calculations. It's just a 2-page paper, and postulated that cracks cannot just propagate at any speed in a material. Speed of sound is obviously a limit, but they will actually only advance to about 40% of the velocity of sound, and then they should start bifurcating. So the crack will pick up speed if it has a mechanism for picking up speed. And then when it reaches about 40% or 35% the velocity of sound in the medium, it won't accelerate any further. It'll just bifurcate. And so this is a nice paper. It's got an innocuous title like Brittle Fracture in Mild Steel Plates. And there was a lot of interest in brittle fracture in mild steel at that time. Ron, it's more in Ron's domain, which is got to do with the Liberty ships. They were failing in the harbor on the middle of the North Atlantic under seemingly benign conditions. And that led to a discovery that iron-based materials can be embrittled if the temperature gets sufficiently low. And sufficiently low is not liquid nitrogen or anything, but a cold temperature on a cold day in the North Atlantic. The second paper was written by a lady named Elizabeth Yoffe. She worked with, her PhD advisor was a person named Orowan, who was was a colleague of Ron, I think, for some years at least at MIT. Orowan was one of the discoverers of a very important concept in materials, or a real defect called dislocation, which explains why metals and other materials can be shaped. It's the basis of this defect is the basis of shaping. And Orowan, Elizabeth Yoffe was Orowan's PhD student in Cambridge, and they wouldn't make Orowan a professor in Cambridge for discovering the dislocation, so he moved to MIT. So that's the origin of his transition from Cambridge UK to Cambridge, Mass. And he had done some. He was very clever. In fact, the Nobel records are declassified now from the mid 1900s and so on. And he, G.I. Taylor, and Griffith, who's also well known in the fracture business, they were all nominated for Nobel Prizes. And in ordinary times, they would have won, but unfortunately, they emerged on the scene just as when modern physics was coming out. So classical physics stopped getting Nobel Prizes after about 1905 or so. So otherwise, they would have certainly been very, very worthy of a Nobel Prize. Elizabeth Yoffe worked with her. I knew her in Cambridge, just an amazing person, very modest. And Orowan had done some simple experiments with some polymer, and he told her that, I think this is what is happening. Cracks can't pick up any speed. There is Mott's paper. So these things will start bifurcating when they reach some threshold speeds. I know this is what is happening. And he said, you go work out the mathematics for this and show that this will indeed happen. And Orowan was of Hungarian origin, very traditional. And so every time he would meet with Elizabeth Yoffe for a research meeting, he would always invite the husband, who was also a faculty at Cambridge, UK. He would be given a cup of tea and asked to sit in the corner of the room while he discussed the research problem with Elizabeth. And then, so Elizabeth Yoffe went and showed that that there is crack bifurcation, and she explained why a crack would bifurcate as the speed increases. It turns out that cracks try to run perpendicular to tensile stresses. So if you pull, a crack will always propagate perpendicular to the pull. It turns out when a crack picks up speed at a certain speed, just ahead of the crack, it sees very many directions in which the tensile pull is equalized. So it's like coming at a fork in the road, and there are 10 forks, and you can choose to go whichever way you want because all are equally easy to run along energetically. And so the crack is given an option. It comes to picks up speed. Suddenly it finds that it can go in 10 different directions because the pull is equally good in all of those directions. And that manifests as crack bifurcation. So Elizabeth showed that. And in fact, the last sentence of the paper above the acknowledgement says, these effects have been elegantly demonstrated by Dr. Orawan in sheets of cellophane, and he's expected to discuss them more fully elsewhere. And as was the case with Orawan, he never wrote up much of his work, or he would publish them in the most obscure of journals. I think he did a paper in German on this, but I haven't been able to find one in English where the paper is directly addresses these experiments that she mentions. Maybe I'm told his correspondences and papers are still housed in MIT, and maybe one of these days, with Ron's permission, I can try to get access and look in. Okay, now coming to to reconstruct the picture of why this thing fragments. So here I'm showing schematics. So we have a drop in A. The interior of the drop is in tension and the outside is in compression because of the way the drop has been quenched in liquid. And then we set a crack in motion in figure B at the tail. And so what happens is the crack picks up speed because it's feeding energy from the tensile stresses in the core of the drop. They are feeding strain energy. So the crack is well fed by energy, so it picks up speed. When it reaches the critical speed of 1600 or 1700 meters per second, it runs into this bifurcation threshold, so it splits. Then each of the split cracks, they pick up speed after feeding into energy from this tension zone. They reach the threshold speed, they bifurcate. So what happens is one crack leads to 2, 4, 6, 8. The process repeats ad infinitum. And as a consequence, what will happen is the whole drop becomes powder. So you start a crack, it picks up speed from this tension, from the energy stored in the tensile zone, reaches the threshold velocity at which it finds it's easier to propagate by bifurcating. So each of these bifurcated cracks then picks up speed, and the process repeats continuously. And we saw the evidence for the bifurcation from the fingers ahead of the crack tip, and then so this is the reconstruction we could do based on the experimental evidence of the cracks hitting a threshold speed and then seeing evidence of the bifurcation. So is that clear? And then eventually this bifurcation goes all the way from the tail to the front, and then the entire core is made of fragments. And in figure C, you see that shown as kind of a dark region which encompasses the core of the drop. So this is why our drops look the interior of the drop is completely dark when the bifurcation. So the bifurcation events are seen ahead at the crack front. We got the crack velocities from pictures such as this, and eventually this bifurcation repeats ad infinitum, and the core of the drop is completely filled with fragments. Usually, when the crack enters the compression zone on the surface, the cracks will slow down because now there's no tensile field. So usually the velocities will drop, and in a few cases we have actually measured the drop velocities in the compression zone. It's much lower, on the order of a couple of 100 meters per second, and then what you saw as fragments flying out, they are only at 25 meters per second. Remember, that is a fragment velocity. What we were talking about at high speeds is the crack velocity. Some pictures of fragments. This is less critical. We see fragments from different portions of the drop, like we did experiments similar to what Hooke did by encasing the drop in glue, in an adhesive, finding out what the fragments look like at the surface versus the interior, what are their ranges, 15 microns to 2.5 millimeters or so. And we can also make some estimate of the stress in the drop from looking at the fragment sizes. There is a small formula in a famous book on glass by Holloway. It's a very nice book. There used to be a series of books that were published in the 60s and 70s. They were written by an expert. They encompass a whole lot of topics in physics, chemistry, and optics, and so on. And each of these books was written by an expert in the field in conjunction with a high school principal or a teacher, so that it would be technically correct and expository. And one of these is called Physical Properties of Glass by Holloway. And it's a wonderful book and tells you all about glass. And he gives this formula. And from the fragment sizes, you can get an estimate of the stress, which is about 160 megapascal. It's not important what that is. That's the stress in the core of the drop. We didn't have measurements at that time, but subsequently I'm going to show you some measurements. So summary of the work so far: cracks propagate with high velocity, reach a threshold about 1700 meters per second. There's a self-sustaining fracture wave from the tail to the head. And then we think we observed evidence of bifurcation, and we think we can explain the bifurcation based on the disintegration based on bifurcation of these cracks. Ron, how much time do we have?
We have about 20 minutes left, but I really would like to. Are you going to show your video?
I'm not going to show the way. I'm going to give you the link. I can play the video, but it would be some rehash of what I've talked today.
I know, but I think it's fun to see. It's only 2.5 minutes. Why don't you show that?
No problem. So I'll skip to the video in a minute, and then next.
I have a question. May I ask a question before you go?
Sure.
I'm trying to visualize that wave, that fracture wave moving through. Is it a compression or a refraction wave?
We believe it's a rarefaction wave because it's feeding energy from the tensile field in the core of the drop.
Okay, so that's what's happening inside. What about in the surface?
The surface, it runs into the compression zone, and the crack decelerates. It almost comes to a stop by the time it hits the surface.
But the surface breaks down because you had essentially expansion inside and it's just pushing it out? Or is it a...
Well, actually, for seeing the surface, what happens at the surface, it's better to look at the picture from the glass... when we look at these glass blocks, they have tension in the surface and compression in the, I'm sorry, they have compression in the surface and tension in the interior. And in these, you can see this, deceleration as the crack hits the exit very nicely.
Well, I mean, I would like to see the video, but you want to do that now, and then we'll get into discussion, because I have a couple of questions too.
Yeah, sure. No problem. I can.
I think it's just worth seeing. Yeah.
I'll just say that then more recently, just 2 minutes, and then I'll move to the video. We had a collaboration with a gentleman in Tallinn in Estonia, who's considered the world's foremost expert on three-dimensional photoelasticity. So this is a technique for measuring stresses, and he was able to measure the stresses within the drop. This shows, the green line shows the stresses in the tail. The red and blue show the stresses within the in the head of the drop, and the stresses are plotted as a function of radius, and you find that in the core, the stresses are quite high, actually even higher than what you see in commercial tempered glass. Auburn developed the theory of 3D photoelasticity in the old Soviet Union in the 50s and 60s, and then nobody paid any attention to his work till glass started becoming popular in bottles and cell phone screens and whatnot, and then they started coming to him to do measurements. And he's really a remarkable gentleman. I think he's still alive. He must be close to 100. Now, if you do the same experiments with the borosilicate, Pyrex, glass drop, you won't see this disintegration. And that's why Pyrex is used in cooking utensils and so on. Pyrex has a low borosilicate has a low thermal expansion coefficient. You don't get stresses. And so if you make a Rupert's drop out of Pyrex or a borosilicate glass, I shouldn't say Pyrex because it's a very confusing situation now with this trade name of Pyrex. Corning sold off the Pyrex trade name, and there's a lot of confusion as to who is calling what Pyrex. So you won't see any stresses in very low stresses in borosilicate, and so you won't see this type of disintegration. It'll behave like an annealed drop. I won't go into the reason why the head is so strong. It's because of the compressive stresses. And then I'll play the video in I think it's 2 minutes. How do we share this?
Yeah, definitely.
Just 1 second. I'm trying to share it.
Yeah, okay.
Can you see the video? No, right?
No.
Okay, then let me do one thing. Just a minute.
Yeah.
Okay, now?
Yeah, go and play it. Now it's ready. Yep.
Okay.
I can't hear anything though. Is there audio?
Okay.
Okay.
Quick, we'll.
Okay, well, we can watch it.
Read it, yeah.
Yeah, it should be on.
I think this is the link.
Okay. You can talk over it if you want to.
Shall I stop here? Or?
Yeah, I guess so, because we can't hear it anyway.
It's about 3 minutes long, so it's better I can stop it.
I'm not sure why we don't have, maybe, why don't we have video audio? I don't understand. Let's see. No, I guess it's on your end. All right, why don't we stop it? I guess you're right.
Okay.
Yeah, I know that everyone has the link, and so they can watch
Yeah,
it.
I think I can share the slides also, so it's not a.
No, it's okay. I mean, we all have the link because it was in the notice
Let's
of
go.
the meeting.
Yeah, 1 second. I'm just going to skip to there are a few things I'd like to. How do you go to the end? Yeah. Just a second, and I should be
Yeah,
done.
okay.
The
Ron, I don't know about others, but when I clicked on the link that you sent with the video, there was no movement. There was a
Oh,
picture.
mine played. I
It
can
did
send it
play?
again.
Maybe I did something wrong. Okay.
Oh, okay.
So I give a bunch of references here for.
Yeah. No, let me let's we got about 10 minutes, 15 minutes. So
Yeah, I'd just like to show this. So this is taken from Samuel Butler. He was a very famous poet at that time in 1663. He wrote a little stanza on these drops. It says, "Honor is like that glassy bubble that finds philosophers as trouble, whose least are cracked, the whole does fly, and wits are cracked to find out why."
Okay.
Yeah.
Well, let's turn to some questions because
Sure.
I want to begin this because I have a couple. First of all, a comment. Yeah, I mentioned the Purdue College of Engineering's 150th anniversary. As part of that process, they've assembled sort of a timeline of important events that reflect on Purdue University's College of Engineering. For example, in 1969, they show Neil Armstrong and, of course, landing on the moon. In 2017, they show Shandy and Prince Rupert's drop because, well, this was monumental in the following sense. You understood, explained for the first time something that is important to all of us in the sense of tempered glass, which is used in our for example, in our windshields. But I have a question. The question is, and you mentioned this, you said if you're dealing with Pyrex glass, you would not see the same phenomenon. But
let me say borosilicate glass.
Hold on. Let me ask my question first. Let me ask, if in fact you were doing with soda lime glass and you tempered soda lime glass, it would be resistant, correct?
If you tempered soda lime glass, it would not break in this manner.
Okay, so my question is, what is it about tempering? What changes during the tempering that leads to the immunity to the phenomenon known as St. Rupert's phenomena? What changes?
The two things. If you temper the glass,
Yeah.
both won't happen. If you hit it on the head with a hammer, it'll break right away.
If it's tempered.
If it's tempered. What I mean, anneal, if it's anneal. I'm using tempering or toughening glass is called tempering. So, so I'm annealing the glass. Then if I hit it on the head, it'll break right away.
Okay.
But if you snip the tail, it won't shatter like what I showed you.
Yeah.
And that's because the annealing gets rid of the stresses in the glass. It makes it stress-free.
But I mean,
So
if you hit the tail in a tempered glass, or if you were to do the same experiment with you used an ignition source to
I mean, it's the same thing. If you hit the tail with a hammer, or you snip it in a piece of soda lime glass that has been annealed, Rupert's drop, then it won't fail in this manner. All the properties are tied in with the internal stresses set up in the drop.
I guess I don't understand that. You're still introducing stress.
No, when we anneal, there are different ranges. Annealing is done. It is heated uniformly and then very slowly cooled. So there are no stresses set up.
So let me just understand. So if you take that product, which is slowly cooled, and you try it and you hit the tail, will the whole thing implode or not?
No, it won't.
Okay, so you
need these stresses that are set up by the quenching process.
I see. Okay.
Right? So
okay. Good. Let's go on to Michael.
Can
There
you hear
go.
me?
Yeah.
Okay.
Yeah.
Yeah, I can hear you.
Maybe very. Let me just look. Okay. I might be able to help here because I was involved very deeply with glass. It would be interesting to know how glass is tempered because you might not believe it's even possible. And basically, the way it's done is let's imagine a 4-foot by 8-foot sheet of glass being held at the top by tongs, self-tightening tongs. So the weight of the glass grips the tongs. You heat that entire glass plate from both sides with a heater to 1200 degrees Fahrenheit. That's the softening point of soda lime glass. At 842 degrees, that's the transition temperature. Any stresses in the glass begin to become relieved. But at the 1200 degree point, now the glass is becoming soft enough to the point where those tongs actually make little divots into the glass.
Exactly.
You then slide that glass out of that furnace between two matrices of a frame. Each matrix has multiple nozzles that blow air out. So you might
Exactly.
have 20 nozzles across and 40 nozzles down, and you cool that 1200 degree glass to 600 degrees within 10 seconds, 15 seconds. So the outer skin of that glass hardens first, and then the internal begins to create the tension. And that glass then is at that point tempered. And if you want to see an example of that, look at the rear window of your automobile, and you can see the circles where those nozzles are, particularly if you're looking through polarized sunglasses.
Oh, I get it.
And if you want to see bifurcation, take a nail with a hammer, tap that glass of your automobile, and as soon as that nail hits it, the bifurcation, you'll dice, it's called dicing, the entire sheet will break up 1/4-inch pieces. It's an interesting phenomenon. Better to do it with just a tempered plate of glass rather than your automobile, however.
I'm intrigued by this because I have a friend who just recently had the rear windshield in her car just spontaneously implode. She didn't hit anything, nothing hit the windshield. It just, for some reason, it just imploded. And I was just curious about how that might happen. Maybe it was improperly tempered somewhere along.
I don't know. I don't. Nowadays, windshields they've gotten away from glass. I don't know if that automobile had a glass winch, but usually they use a polymers sandwich.
Okay, all right.
The windshield is laminated. It's not tempered.
Yeah. Well,
with a plastic between
between the layers,
pieces of glass.
All right. Okay. Is that typical of the rear windshield or both windshields?
No, just the front windshield is laminated. The back window, and probably the side windows are tempered.
Okay. It was the rear windshield that just imploded spontaneously on her. So anyway, let's go on. We have a question from Avi.
I seem to remember in high school, where the science teacher, physics, had what I recall as being something shaped like a flask. And my recollection is that he took it and he pounded a nail into the board, and it held. And then he took, I think it was a little pebble, and he dropped it into the mouth of the flask. And as it hit the bottom, the entire thing disintegrated. I have no idea how he did that magic. And I don't know if it's related to what we're discussing here. My knowledge of material science is very meager. So does this ring any kind of bell with anyone? If so, how is it done?
I mean, maybe Michael is, but there's an interesting story. One of my colleagues, he was my boss's boss here, and he had gone to Corning, and they gave him one of those what is it, Corel bowls, and said that, you know, you can drop it on the floor from some height and it won't break. So I used to meet with him on Saturdays with his students, and he used to make me a cup of tea. So always he boiled the tea in the corral, and then he told me, you know, this is so resistant to breakage, and I'm going to drop it and show you. And before I could tell him, hold, please don't do it, when the heated state, he dropped it and it shattered. And he was a little bit taken aback that it did. I told him, you know, this won't shatter if you drop it when it's not heated, you know, but when you heat it and drop it, it would shatter. I don't know if in your particular experiment there was some bottle was heated or whatever that you described. It was a little bit embarrassing for him because he said this won't break, and he just dropped it and it just broke into dozens of pieces.
So
Well,
the-
this memory is from more than, well, high school years, a long time ago, so I'm not sure I remember it correctly, but the reason it stayed with me is it was such a vivid experiment. So, you know, just a fantastic thing to have happen. I don't know how it was done.
It's interesting. Interesting observation, Avi. So let me put some perspective in this question. So Prince Rupert discovered or this experiment first occurred in like 400 years ago. When did people become clever enough to commercialize and lead to tempered glass, for example, for automotive surface? When did that transit? How long did it take for the
That,
community to get
to my
there?
knowledge, the automobile windshields applications occurred in the late 20s or early 30s.
1920s or 30s. Okay, all
Mhm.
right.
And then there was another way of strengthening glass, which is the more preferred way in certain cases, especially with complex shapes, is by ion exchange.
I see.
So you replace the sodium ions in something like soda lime glass with potassium and other ions, and you can put compression or tension depending on the relative sizes of the ions that you're exchanging.
Yeah, it is windshield glass. Is it actually soda lime glass, or is it more? Is it soda lime glass, Michael? Yeah. You're muted, Michael.
Yeah, the windshield is soda lime glass. Borosilicate is quite expensive.
Yeah.
The difference is that borosilicate expands at a number of 86, and I think that's 8,600 millionths of an inch per degree centigrade is the
Yeah.
expand, and borosilicate is 33. So there's quite a bit of a difference.
Yeah,
But
it's a huge difference in thermal expansion coefficients, and that is the origin of this. One of the causes of the residual stress, the magnitude.
And Michael, one other question. What is the benefit of the lamination? Is that to absorb impact, or what?
It's so that you don't go through the windshield. It doesn't shatter and cut. It's more likely to just crack, and that internal lamination holds it together. It's a safety.
I see.
I know, Ron, the lamination acts as a barrier to the crack propagation.
Gotcha.
So when the crack hits the lamination, it's arrested, much like in a composite material.
Yeah, no, I mean, I think I would guess that just about everybody online has had experience with cracked windshields at some one time or another. And I know that I've had a couple of incidents where, you know, the windshield, it didn't crack throughout, but where it cracked, it fragmented. You could see small particles of broken glass still intact, but had to be replaced.
Oh, Michael, are you from were you involved in the glass industry?
I was producing artistic images in engraved plates of glass. So I would engrave an annealed plate of soda lime with an artistic image, fuse another plate to the back, and introduce plasma, neon, argon, xenon, helium between those glass plates, and electrify them to produce images. So a lot of my work, it took years to understand it all, was dealing with flat plates of glass and high temperatures, annealing, etc., and laminating them with, we were using frits, non-vitreous frits to do it.
Okay. The reason I asked was if you were recording or something, one of my close friends, Chuck Kirkshian, we call him Mr. Glass. He lived in Portland, Maine after retirement. And whenever we had a question about glass, he maintained a glass network. And he's a graduate of MIT, Ron, student of, I think, Ali Argon in late 1950s. And then, sorry, and something. And that is a Science magazine in 2017, I think, ranked it as one. They made a video on this and ranked it as one of the top 5 of that year. So,
that's great. Well, I want to, Shandy, I think I promised you we'd finish by noon, and it is just about noon.
okay.
So I want to thank you for an illuminating presentation on something we're all familiar with, even though we didn't understand or appreciate that this all began so many years ago, 400 years ago. It's really quite amazing where the technology has gone since St. Rupert or Prince Rupert first detected all of this. But I want to thank you for joining us today. I want to end with a very familiar refrain that I've picked up during my travels to Purdue, and that is boiler up.
And hammer down on
Yeah,
the drop.
there you go. You might just explain. Do you know the origin of boiler up, Chandy?
I know the origin of boiler. I don't know what does boiler up mean.
Okay. Well, I know that every time I'm on campus, when somebody does something good, the comment is boiler up. So we'll have to figure out what
supposedly
that is.
Purdue started as a training school for locomotive engineers and so on, railroad engineers.
All
So the
right.
boiler
Gotcha.
name came from that. I don't know what is boiler up and hammer down. All I know is you hammer on the drop and it's dead.
Yeah. Okay.
Okay.
All
There's
right. Well, look.
Well, it's the Boilermakers, right? The Purdue
Yeah,
Boilermakers.
that's
Yeah.
exactly. They are the Boilermaker. I think it had, Avi, I think it had something to do with the wife of the coach of the football team. They were having a bad season.
Yeah. Some story like that.
Season, and she said, well, we got to get some inspiration. So she coined the word boiler up. I think that's how it comes about. That wasn't this past season, which was bad season. But nevertheless, I think that's the origin. I'm not sure
Maybe
though.
it was just her nickname.
Yeah, it is. Anyway, boiler up, everybody. We'll see you in 2 weeks.
Sorry, I went over time, Ron. I'm very sorry. I think I went over time or whatever.
No. You're right on time. That's perfect.
Okay.
Thanks, everyone.
Thank you all, and wish you. Today is Valentine's Day, and we give you love with Rupert's drops.
Yeah.
Happy Valentine's Day.
That's a good reminder. Don't forget it's Valentine's Day, folks. Take care.
Okay, goodbye.
You bet. Take care.